We are Team Propeller, and we've had the opportunity to work with the Solar Splash team to enhance the efficiency of their boat's propeller. Our goal is to optimize their current traditional propeller design with a toroidal shape. Our project consists of testing, simulation, and multiple rounds of optimization to examine thrust, torque, RPM, and efficiency of a toroidal propeller. As defined in our problem statement, efficiency is kT over 2 pi kq, where kT is the coefficient of thrust and kq is the coefficient of torque.
According to research conducted by MIT and Sharon Marine on toroidal propeller, it indicates that toroidal design can improve propeller's efficiency up to 105%. So, we find there is a gap to improve the Solar Splash design, which can have a better performance in the competition. In this case, there are three main deliverables that are going to deliver to our customer, which is Solar Splash. First is the operational full-size propeller prototype that can fit onto the existing motor. Second is a technical report with testing data, procedure, result, and analysis of the propeller. Third is a theory of operational manual. As you can see from the right top of the screen, this image is coming from the manual, which indicate how the propeller should be mounted on the motor safely. And we also provide some safety protocols to avoid any incident to happen. We also have several requirements and specifications in order to satisfy our customers' expectations, and those are decided at the early stage of the semester.
So here we have a quick overview of the propellers involved in this project. The first one on the left is the current traditional propeller used by Solar Splash before the onset of this project. And then from left to right, the other three are in chronological order of the toroidal designs that we've made throughout the semester, with the first one being an initial conception mainly for the purposes of demonstrating the feasibility of manufacturing, and the yellow one on the far right being our final design. The CAD generation was a key component of this project. We needed to create a CAD model that was easily adjustable, something that we could manipulate certain parameters quickly and easily so that we could quickly iterate and optimize our design without needing to go back into the CAD back and forth between our simulation software and our CAD modeling software. So in order to do that, we started by 3D scanning the original Solar Splash propeller. And then from there, we were able to extract the hub geometry and import that into a new model creation so that we could ensure that the new model would properly connect to the current motor and setup of the propeller. One of the key components of this design is the cross sections of the blades. They are defined by NACA airfoils. Here you have the equations that govern the profile of the NACA airfoils. Using these airfoil shapes enhances our ability to control the aerodynamic qualities of the propeller blades, like the lift and the drag. So in the end, we ended up with a model that has quite a long list of parameters, as you can see here. These parameters are all numeric values that we can manipulate independently, so that we can import them into our CFD model and change them in there so we can cycle through design iterations quickly. These values dictate various locations, lengths, curvatures, and angles that define the overall geometry of the propeller. And as you'll see in the coming slides, we used this parameterized model to iterate and optimize using our CFD.
So a big part of this project was the optimization that would have to be done on our toroidal propeller design, and this meant that we would have to go through multiple different iterations of design. So we decided early on that the most efficient and economical way to go about this would be to create a CFD simulation that we could relate to our testing rig instead of having to 3D print and actually test every iteration we came up with. So to make this simulation, I followed a tutorial under Star CCM called the Marine Propeller in Open Water. And then I adjusted that tutorial to meet the needs of this project. So one of the main adjustments I made was the geometry that was entered into the simulation. I created the geometry as an assembly in NX that's made up of a rotating region and a static region. And this made it so that I could sub the new geometry for each toroidal iteration fairly quickly without changing anything else in the assembly. I could then transfer the design data from NX to Star CCM, and that includes the geometry and the associated parameters, which we would need for optimization later on. And then once geometry was in, I could build the simulation around it. And I did that by following the tutorial to create boundary conditions, the regions, and then create the mesh. And then the only change I really made to the mesh was I made it denser around the edge of the far field and in the area immediately surrounding the propeller, just to better capture the flow conditions there. So one of the main limitations to the simulation is that it has different assumptions than our testing rig. Our testing rig is done in stationary water, while this is an open water setup, which means that water is actually flowing past the propeller as it's rotating. And you can see that in this photo here, which is the vector velocity field of the water as it flows through the region. And I defined the speed of the water as the advancement velocity of the solar splash hull, which is defined as 1/2 times the square root of the length of the water line. Another limitation is that this is a very idealized model, which means it assumes a very smooth surface finish and that there's no deflection of the blades when it's rotating. We still decided to move forward with this simulation despite the limitations because the open water standard we believed would more accurately capture the operating conditions of the propeller when it's on the solar splash boat. So once we created the simulation, the next step was to correlate our testing and simulation data. And this was done by running a series of tests on the solar splash propeller and our first toroidal iteration across a variety of RPMs, and then outputting the thrust. And then I took these RPMs and put them into the simulation and also output the thrust. And then as you can see in these graphs, it's a thrust RPM curve for both of the models for both simulation and testing. And what we were looking for here was that the data just followed similar trends. And as you can see, like as RPM increases, the thrust is also increasing across both propellers for both simulation and testing. So from these trends, we made the assumption that if we see an increase in efficiency in simulation, it will be matched by an increase in efficiency in testing, although we are not sure of the exact magnitude.
Now we are going to talk about the testing. I designed a testing rig that consists of an uniaxial slider, a constraining rope, and a mounting structure, which allows our motor to move freely under the propulsion. When the propeller is running, it makes the setup to move, and which is moving rightward to the image shown here. At this moment, the rope will constrain the movement, which we can get a reading of the thrust from the fish scale due to the force balancing, as the orange part in the figure. Also, in order to get rid of excess displacement, we also did finite element analysis to the panel, showing on the right side of the screen. This will make sure that the condition of the panel after we put on the motor will be fine and provide enough testing data.
When conducting testing, we use two different procedures to obtain the final efficiency results. For the first procedure, we use the Vetter electronic speed controller, also known as the VEST tool, to gather data on the thrust of each propeller at different RPMs. The VEST tool is essentially a controller allows us to input the amperage we wanted to run the motor at. This VEST tool would give us an output of RPM for each amperage. And ERPM is an electrical measurement, and so we converted ERPM to RPM of the motor using the equation below. After finding the RPM of the motor, from this equation we use the gear ratio, which is the ratio between the number of drive shaft revolutions for one revolution of the propeller, and converted the RPM of the motor to the RPM of the propeller. The gear ratio we used is 0.58, and this was given to us by Solar Splash in their 2019 technical report. Conducting this test allowed us to measure the thrust values generated by the propeller for each RPM, which was important for calculating the coefficient of thrust, since it is in our equation to calculate efficiency. With this test, we weren't able to calculate torque, which is needed for the coefficient of torque, which is the second half of our efficiency equation. Therefore, we had to come up with another procedure to measure torque. So for the second procedure, we used a power drill setup and a push-pull scale to measure the torque and thrust across various RPMs simultaneously. And we attached the power drill to the coupling of the motor. So in this test, pretty much the power drill is what is driving the propeller instead of a set of batteries powering a motor. As the propeller rotates, there's a reaction force acting on the propeller, essentially trying to rotate the power drill in the opposite direction. To measure this resistance, which represents the torque generated by the motor, we use the push-pull scale. The hand of the power drill acted like an arm, so to get torque, we applied the push-pull scale to the end of the arm, which was approximately 6.5 inches. And the push-pull scale then registered the amount of force required to resist the rotational motion of the power drill, and the torque was found using the moment equation. Then from there we used a simple calculation, as the previous procedure used the gear ratio to convert the torque of the propeller to the torque of to convert the torque of the motor to the torque of the propeller. And then finally we calculated the coefficient of torque from the equation below. It's important to note that the results from the second procedure were somewhat less accurate due to inconsistent setup and measurement errors. With that being said, with these two procedures, we were able to get the coefficient of thrust and torque and calculate the efficiency.
So once we had set up the testing rig and had our first iteration of the toroidal propeller completed, we could start the optimization of the toroidal propeller. So to do this, we used the Taguchi method to produce orthogonal arrays because that will minimize the combinations needed to map the trends of each parameter. And we chose this method because, as Henry said, there are many different parameters designed in the NX model, and it would be very time-consuming to go through and optimize all of them. So this is an example of a third-order 11-parameter Taguchi array that we did, and from this we could identify the most efficient value for each parameter, and we then put that into the simulation. However, when we simulated this, we found that the efficiency actually dropped very low, and we hypothesized that this was because the parameters are very dependent on each other, so this might not be the best method of optimization. So instead, we went back to the orthogonal arrays and chose the one with the highest efficiency and 3D printed that, and that's this blue propeller that you can see here. In testing, however, the increase in efficiency of simulation did not map to the testing rig, and we believe that this was because of the very low thrust output by this propeller. So instead, we switched to a constrained optimization where we ranked all of the simulations we had done based on efficiency and then pulled out any of them that had thrust below the threshold of 170 newtons. And then we looked at the parameters of all the models that were left and then created this yellow model seen here, which is our final toroidal iteration. So in simulation, this toroidal propeller had slightly less efficiency than the solar splash propeller, but it had much higher thrust, which we believe would make it perform much better in testing.
So our final testing results, as seen in the top graph, indicate that the toroidal propeller had a higher efficiency at speeds lower than 250 revolutions per minute. However, after this speed, the solar splash propeller had the highest efficiency. This result is from the fact that the toroidal propeller's torque starts to significantly increase, as seen in the middle graph. We wanted to include the local maximum propeller in these graphs because it had the highest efficiency in simulation compared to all other propellers. However, as seen in the top graph, it produced the lowest efficiency in the physical test. Even though it produced the lowest torque, it also produced minimal thrust. It was from this observation where we focused on increasing thrust as much as possible, yet keeping efficiency at a low. This is where we came up with our final toroidal design, as seen in the yellow image. Even with the newest optimized model, our final testing results indicate that we did not meet our efficiency improvement specification of 10%. However, we hypothesized since the beginning of the project that the aluminum manufactured propeller would perform better than the 3D printed one used in testing because the blades would experience less deflection. To quantify this, we ran an FEA on both the plastic 3D printed model and the aluminum one using the pressure loads outputted from the simulation running at 5.5 revolutions per second. We found that the aluminum model has around 97% less deformation than the plastic one. A lower deformation will increase the thrust produced by the propeller, thereby increasing efficiency.
So if we were to do this test again, the first thing we would want to change is our testing setup. We use a cattle trough as a tub for testing, which does not replicate open water conditions since the water is stationary. Another thing we would want to change is the way we tested torque. Using a torque sensor would eliminate much of the human error from our previous technique, giving us more accurate results. The next thing has to do with manufacturing. We had an issue with manufacturing time, so having a larger and more flexible budget would have allowed us to 3D print the final propeller out of metal.
Another one of the limitations of this project was a slight lack of preliminary specifications. If in an ideal case, we would have had access to the motor power curves and the hull characteristics, which would allow us to essentially optimize the propeller to a specific RPM and required thrust to move the boat at its optimal speed. That information, however, was unavailable, so we had to run with an unconstrained optimization. So in the future, there's opportunity there for improvement with those preliminary specifications. Additionally, the time constraints and computational constraints on this project limited the number of parameters we were able to test overall. There were several parameters that we were unable to map the efficiency curves for due to a lack of time. And finally, we would like to thank various faculty at the University of Rochester, including Jim Alkins, Bill Mildenberger, Chris Pratt, Professor Muir, and Dr. Muhammad. Thank you.